Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University Gwalior. Today we are going to discuss about the module extraction methods from the paper Fundamentals of Analytical Chemistry. So in this extraction methods, we study here introduction to extraction. What is extraction? Extraction may be liquid extraction or it may be solid phase extraction. Then what is the theoretical concepts behind extraction we shall study here. Then by using these extractions, how separation of mixtures can be done by taking mixtures to immiscible mixtures, how a solute can be taken out from one solvent to the another solvent. Extraction is an analogous separation process in which a solute is distributed between two immiscible solvents. A law defines the ratio of the concentrations of the solute in the two solvents, 1 and 2. Kd is equal to C1 upon C2, where Kd is the distribution coefficient or partition coefficient, a special type of equilibrium constant which is related to the relative solubilities of the solute in the two solvents. One solvent is water and the other is an organic solvent because the two solvents should be immiscible, so that inorganic ionic species as well as polar organic compounds are found largely in the aqueous phase, while non-polar organic compounds are largely in the organic phase. This is another way of saying like dissolves like. In dilute solutions, to a first approximation, the distribution coefficient is independent of concentration. It can be further explained by taking an, for example, suppose we are separating the excess fatty acids from a sample of toilet soap. A pair of solvents such as ether and water are effective because fatty acids are far more soluble in ether than in water, while the opposite is true for soap. If ether is defined as solvent 1 in equation 1, then Kd is very large for fatty acids and very small for soap. In equation 1, phase 1 appears in the numerator and phase 2 in the denominator. Often the organic phase is placed in the numerator, but just as often the lighter phase is placed in the numerator. Thus, the assignment of phase number is very arbitrary and must be clearly stated to avoid any ambiguity in quoting values of the distribution coefficients. The distribution coefficient pertains only to a single species and does not include possible products of side reactions. For example, the extraction of benzoic acid HB from water into an organic solvent such as ether. Figure 1 explains the equilibrium situation for which complications may arise if the aqueous layer is not acidified and the benzoic acid dissociates. As shown in the above equations, two independent equilibria as illustrated in figure 1b, note that the partition equilibrium pertains only to the undissociated benzoic acid molecules in the two phases, and that the dissociation equilibrium pertains only to the species in the aqueous phase. Benzoic acid does not dissociate in an ether solution. So in the figure 1, it has been explained the distribution of benzoic acid between ether and water and between benzene and water, and in C in an extraction. It has been taken in three different stages: HB between ether and water in A and B, and between benzene and water in C in an extraction process. A second complication arises if benzene is used as the organic solvent in place of ether as shown in figure. Benzoic acid is partially dimerized in benzene as according to the following equation 4. In extracting benzoic acid, anyone will like to know how much benzoic acid is in each phase. The expression which takes all forms into account is called the distribution ratio D, and the distribution ratio D is equal to total concentration of benzoic acid in organic phase upon total concentration of benzoic acid in aqueous phase, represented by equation 5 and 6. In this particular case, one can make substitutions as follows from equation 3, and we obtain equation 7, 8 and 9 as shown in the following equations. Equation 3 shows that the distribution ratio can be changed by the simple expedient of changing the pH of the aqueous solution. In acid solutions, D will be large and benzoic acid will be found largely in the organic layer. In alkaline solution, D will be small and benzoic acid will be found in the aqueous layer. Expressions similar to equation 9 can be derived for other types of side reactions, for example, formation of ion pairs or metal complexes in either or both phases. If the side reactions involve ionic species, one can assume that ions exist only in aqueous layer or in a very polar organic solvent. If the distribution coefficient is very large, a single extraction in a simple separating funnel will remove all of a solute from one phase to another. However, it can be shown that for a given amount of extracting solvent, it is more effective to divide it into several small portions and use each portion successively rather than to make a single extraction with all of the solvent at one time. It is always advantageous to make extractions by taking a small portion of the solvent at a time, and a number of extractions should be made. For example, assume that 4 gram of butyric acid is to be extracted from 500 ml of water with 500 ml of ether. The distribution coefficient for this system is 3 at 25 degrees centigrade. If the ether is used in a single batch, the following equation is applicable, where X is the weight of butyric acid remaining in the water layer. Thus, X is equal to 1 and 3 gram is extracted into the ether layer as shown in figure 2. However, if the ether is used in two successive 250 ml portions for the first extraction, then equation 11 applies. In this case, X is equal to 1.6 gram remains in the water layer and 2.40 gram is found in the ether layer, which is then removed in the second extraction with the remaining 25 ml portion of ether as equation 12 applies. After second extraction, X2 is equal to 0.64 gram remains in the water layer and an additional 0.96 gram is extracted by the ether. Thus, a total of 2.40 plus 0.96 is equal to 3.6 gram has been extracted, which is a significant improvement. Is very clear from figure 2. Comparison on extraction procedure for butyric acid is given here. So, from this figure, it can be very easily interpreted that how in ether layer and in water layer, butyric acid in ether and butyric acid in water, it can be extracted from one phase to another. It is a separation technique, solvent extraction is a separation technique, and we are extracting the substance from one phase to another. For that purpose, we are taking portions of the solvent, small portions of the solvent, and each time we are repeating it. For example, for the sake of explanation, if I say, suppose for explanation I consider I take another value. If 10 grams of butyric acid is to be extracted from 500 ml of water with 500 ml of ether. So every time, if at a time, suppose half of the butyric acid comes to the ether phase, it means 5 gram has been extracted into the ether. In the second successive extraction, again half of the 5 gram, 2.5 gram will come to the ether. Again, in the next successive extraction, 1.25 gram will go to the ether. So, if we go on repeating the process, ultimately whole of the butyric acid will be extracted in the ether portion and a negligible portion will remain in the water. So, this is the basis of solvent extraction in very simple terms, and this can be evaluated in the form of different equations. This process has been shown in figure 2 how by taking butyric acid in butyric acid, ether and water and every time mixing it properly in a separating funnel, shaking vigorously, then taking out lower layer, that is the water layer, and then adding another layer. So ultimately all the butyric acid will come to the one solvent, that is the ether. Similarly, if our solute is soluble, more soluble in water in comparison to organic solvent, then it can be taken out into the aqueous phase by successful intermixing of both the solvent, which are immiscible and forms layer in a separating funnel. The value of extraction is the possibility of separating two or more substances based upon a difference in their distribution coefficients. If one solute has a K much greater than 1 and the other much less than 1, a single extraction will cause nearly complete separation. This circumstance will arise only if two solutes are very different chemically, in which case the pair could no doubt be separated easily by some other method. If two solutes have similar but not identical distribution coefficients, a single extraction will cause only a partial separation with an enrichment of one solute in one solvent and an enrichment of the other solute in the other solvent. If we are to make an adequate separation, we must repeat the process many times. After the first extraction, each phase may be further equilibrated with a fresh portion of the opposite solvent by a systematic recycling of the various intermediate fractions. Its satisfactory separation can be eventually be achieved at a cost of considerable amounts of solvent and numerous manipulations. Lime and Craig has developed a machine to perform these operations semi-automatically. What is this Craig apparatus? The Craig apparatus consists of a series of separate vessels connected so that the outlet of one vessel flows into the inlet of the next. Each vessel consists of two chambers connected to each other as shown in figure 3. The operation is begun by introducing through inlet A an amount of the heavier solvent which will fill chamber B somewhat less than half full. Each of the vessels in the train is filled in a like manner. The sample to be separated is introduced as a solution in the lighter solvent into chamber B of the first vessel. The assembly is rocked back and forth through an angle of about 35 degrees around pivotal P. After equilibration has been achieved and the solvent separated into two layers, the assembly is rotated 90-degree clockwise. The lighter solvent flows through connecting tube C into the chamber D, while the heavier solvent is trapped in the lower part of the chamber B. When the assembly is rotated back to its original position, the lighter solvent, now in D, flows through outlet E into chamber B of the next stage. Hundreds of these assemblies can be mounted side by side or in banks, and all of them rocked and rotated simultaneously by a motor timed to operate as indicated. As you have seen, that by taking immiscible liquids in separating funnels, they are vigorously shaken, and solute partitions between solvent 1 and solvent 2. And the condition is that both solvents should be immiscible. And by mixing them, by shaking well, we take out a portion of the solvent where solute has come. Then we take equal another portion of the solvent, fresh solvent, then we take it out, and by using that we separate the solute from one solvent to the another solvent. From a mixture we may take out one solute, we may take out first. And this is the extraction process. This is the basis of our different types of chromatographic processes. So for making that process effective and less time consuming, a Craig machine has been very powerful and used for the separation purposes, particularly in biochemistry and chemical reactions. Used for extremely difficult separation of substances that are chemically very similar. It is very difficult to separate substances which are chemically different, whose properties are chemically different. They can be separated by precipitation reaction. We can separate one by separation, one by precipitation, other remains in the solution. But these substances which have very closely similar chemical properties, to separate them is very difficult, and that can be done by solvent extraction using the Craig process. In order to describe the operation mathematically, we will use a schematic representation of the machine as shown in figure 4. Here in 4, machine has been shown here, apparatus for the Craig process, where compartments 0, 1, 2, 3 are there. Number of compartments are there where separation takes place. How separation takes place, that I shall explain you here. Consider a series of vessels Consider a series of vessels numbered consecutively from 0 to 4 to 5 to 6, as you have seen in figure 4. Each vessel is of the same size and initially half filled with the heavier solvent to be used. For example, here we have taken solvent S. There is also a series of connecting tubes and valves. No mixing is allowed during the transfer. We will follow the course of a single solute. The arithmetic will be greatly simplified if we assume that each occupies half the volume of the vessel and that Kd of the solute is 1. First, we introduce the sample dissolved in the first portion of the lighter solvent M into vessel named as 0. After equilibration, one half of the solute is in the upper phase and one half of the solute in the lower phase S. The upper layer, solvent M, is then transferred to vessel 1 and a fresh portion of the solvent M is added to vessel 0. After equilibration, one quarter of the solvent is now found in each phase of each vessel 0 and 1. Next solvent M in vessel 0 and 1 is transferred to vessel 1 and 2 respectively, along with a fresh batch of solvent M to vessel 0. The pattern of the operation has now been established and the distribution of the solute develops as in figure 5. Here, as in shown in figure 5, that number of vessels are there and they are being transferred from one to another, upper phase, lower phase, heavier phase, and then the solute is being taken out at every step and it goes to the process is being continued. To start the operation, the sample dissolved is introduced in the first portion of the lighter solvent M into vessel O. After equilibration, that is shaking and settling, one half of the solute is in the upper phase and one half in the lower phase S. The upper layer solvent M is then transferred to vessel 1 and a fresh portion of solvent M is added to vessel 0. After equilibration, one quarter of the solute is now found in each phase of each vessel, O and 1. Next, solvent M in vessel O and 1 is transferred to vessels 1 and 2 respectively, along with a fresh batch of solvent M to vessel O. The pattern of the operation has now been established and the distribution of the solute develops as explained in figure 5, in which the vessels are labeled across the top and the number of transfers labeled down the side. In figure 5, you can see the successive distribution of solute in the crack process. Fraction of the total solute in each layer of each vessel for Kd is equal to 1 and Vm is equal to Vs. So you can see here that in the original distribution, after first transfer, how much amount is distributed, then after second transfer, how much amount is distributed, after third transfer, and after fourth transfer, it is 1 by 32, then 3 by 60. So now at every time, this amount is varying and extraction is being done. It may be summarized that with a separation factor of 2, alpha is equal to Kb upon Ka. 8 transfer give only a partial separation of the solute. All vessels, except the first, contain significant amounts of both A and B. After 200 transfers, the separation is not complete, but probably adequate for most purposes. Vessels 80 to 117 contain nearly all of solute B, and vessels 118 to 155 contain nearly all of solute A. Vessels 112 to 123 could be discarded to obtain a higher purity but with a lower yield. Another 100 transfers would improve the separation but would increase the time and the amount of solvent required. The concentration of the solutes decreases with an increase in number of transfers. With 8 transfers, the vessel at the center of the peak contains about 25% of the solute. With 200 transfers, the maximum amount of the solute in one vessel is only about 6% of the total. After 8 transfers, the solutes are spread over 8 vessels. After 200 transfers, each solute is spread over approximately 50 vessels. The peaks become broader with an increase in transfers. However, the solute occupies a smaller fraction of the vessel's use. The solute is never completely removed from ever the first vessel, although after the first few transfers, the amount remaining in the first vessel may be neglected. If the separation factor had been 1 is to 1 instead of 2 to 10,000, transfers would be required to achieve the same degree of separation, not very practical even with an automatic Craig machine. Separations of this type are readily accomplished by chromatography. In the Craig apparatus, one solvent moves with respect to the other in a discontinuous fashion. Imagine now that the size of each equilibration vessel is reduced until the entire system becomes a single column and that the extracting solvent is passed through the system continuously. If both solvents are restricted to thin layers, it is possible to approach an equilibrium state at all points in the apparatus even though it is not exactly attained anywhere. Instead of a series of discrete vessels, it is convenient to construct a column packed with some porous material which will hold one of the solvents stationary on its surface while allowing the other solvent to percolate through it. The stationary solvent need be fixed in position. It is only necessary that the two solvents pass through each other, exposing a large interface. Thus, the term countercurrent is appropriate. In this way, an extremely large number of equilibrations can be achieved without expanding the apparatus unduly. The relationship of continuous countercurrent extraction to the discontinuous Craig process is much the same as the relationship of continuous fractional distillation with a packed column to the ideal bubble cap plate distillation. Hence, it is common to refer to the theoretical plates in a continuous extraction column. Here, this expression refers to the number of separate equilibrations and transfers which would have to be done in order to achieve the same degree of separation. Actually, countercurrent extraction is identical to one form of chromatography. So, students, the importance of separation in chemistry is very well known. You already appreciated what is the importance of separation in chemistry. For example, if in plant products, if in a flower, you want to know what are the different constituents of that color. If a flower is of red color, then you want whether it is a single, whether this is a single component or it is made of 3 or 4 components. So in that case, you have to separate them. All colors have to separate them. For that purpose, initially we have different types of separation techniques. In earlier separation tech was the boiling point or boiling the substance, and depending upon the boiling point of a different substances, because each and every substance has different boiling point. On the basis of boiling point, a substance used to be separated, but there are a problem in separating on the basis of boiling point, because we have to boil the substance, we have to provide the substance, and then heating, the nature of many substances will change, particularly of natural products, of proteins or amino acids. Their nature will change. So we require a method in which energy is not to be provided, or we can safely extract one substance from the another. Another method used earlier was fractional distillation. After boiling, it was fractional distillation. Again, in distillation, we have to heat the components, heat the solution. But in the extraction, whether it is solid phase extraction or liquid extraction, which you have studied in this module, here the separation is very safe, and this technique is very important. And also, this extraction, liquid extraction, is the basis of the technique which you will study or you have studied, that is the chromatography. Extraction is taking place at every point, at every particle. So, extraction in chemistry is a separation process consisting in the separation of a substance from a matrix. It is a basic technique in chemical laboratories where it is performed using a variety of apparatus from separative funnel to countercurrent distribution equipment. This type of process is commonly performed after a chemical reaction as a part of the workup, often including an acidic workup. Thank you.